And then finally, Sydney talked about wavelets, but there's crazy representations that are very exciting and important, way beyond Fourier and wavelet type representations. Sydney mentioned curvelets, there's contourlets, surflets, surfacelets, all kinds of very important new transforms that will be being used more and more in the future. Okay, so this is my kind of outline of some of the ideas I'll talk about. So by geometrical data, what I mean is there's some sense of smoothness in some dimension. So what I mean is you normally wouldn't think about doing signal processing on the surface of an object, but it can be very, very important to think in terms of doing the kind of things like Sydney talked about, wavelet transforms, and actually build up multi-resolution views of three-dimensional objects. That has clear geometric structure because the exteriors of objects have very strong geometrical structure. I think that's kind of clear, right? Just look at anything around you. It's got a solid exterior, and there's some smoothness, right? There's some smoothness along the surface. Okay? That's the same thing when you think in terms of images that have edges. So look at the edges here formed by the cameraman standing in front of the background. There's a certain smoothness to this edge, which is exploited all the time in signal processing. This is a seismic trace. Here's where the oil is. Okay, so when you go to work for an oil company, that's what you get really good at looking for. No oil here. Okay, maybe gas, lots of oil here. Clearly, there's a strong geometrical structure here to this data of some kind of smoothness or continuation of these horizons of the Earth stacked up one upon another. Okay? Lots of other kinds of data. If you think in terms of an airplane maneuvering through space, it has a smoothness along the track of the airplane. Or if you think in terms of a fish tank with water below and air above, there's some smoothness to this data. So increasingly, we're going to do things like signal processing with these kind of data sets that are much even broader than the kind of things that you've been learning about in this course. Okay, does this make some sense? Hopefully. Okay, so what's all this added up to? This is really what I talked about earlier, but there's really two themes or two pressures in signal processing. The first is we're pushing the limit on resolution. We want better and better sound quality, better and better image quality. We want better and better video quality. So we're pushing higher resolution, which means more bits, right? More numbers to describe our data. But we're also trying to process more things at the same time. We're trying to process databases of images, right? We're doing face recognition. We're trying to do three-dimensional television. So we're basically, think of multiplying this number, the number of bits per image, maybe millions of bits, by millions of images in a database of images. You think of a picture of every person in Vietnam, right? From multiple angles, so that when they walk to the bank and they try and get money, they just get the money because the bank recognizes them, right? Okay, these kind of things are coming, but that's millions times millions, which is billions and billions of bits that are going to be needed to describe these kind of systems. And the word is deluge. You know what the word means? It means like rainstorm, big time rainstorm of data. Way too much data, more than we could ever do anything with. And so we need to figure out ways to use signal processing to extract the information from this data without trying to store all of this kind of stuff. Make sense? Okay. Keep going. Okay, so one of the keys to making this happen, and this is a colleague of Dr. Doe, is multi-scale analysis. So you saw Sydney's talk, but the critical thing is the idea of analyzing data at multiple different scales. Okay, just think for a second. If you really need to understand the very fine structure of the beard on this person, then you need a very high resolution image. But if all you really need to do is figure out if it was a man or a woman, this picture might be perfectly adequate, right? And this is much smaller than this picture. So the idea of multi-scale analysis is to adapt the scale that you need to solve the problem, the scale of the data representation to the problem that you're trying to solve. Okay? And the nice thing about wavelets, which this is Sydney's 1 hour talk in 1 minute, is basically we just take an image and we zoom away from the image. We just step back from the image. That makes it smaller, that gives it less resolution. And what do? We take the information we lose. Clearly there's more information here than here. Does everybody see that? Right? There's more information in this picture than this picture because there are more details. We lose details going from here to here. So the thing that we do, these wavelength coefficients, are the detail information that we store, or that we lose rather, going from here to here. Okay? And so the nice thing about wavelets is that given this picture, very low resolution, and this information, we can build up this picture. Given this picture and this information, we can build up this picture. So the critical thing in wavelets is you never need to store all of these images or data sets at different scales. You just need one data set and then this difference information at each scale. Okay? It's very powerful because this information might be very sparse, not very much information. Okay, so I'm going to talk about some applications, and let's start with imaging. How many people know about imaging? You? Okay, so imaging. Imaging is seeing inside someone's head. Okay, for example. And I should have a picture of Dr. Doe here, but I don't. We might try and find out why this student is so smart. So we like to look inside their brain. Right? So there's two ways that you can do this. The first is the old school way. And they used to do this in France. And you take a big knife and you cut their head open and you look inside. The problem is it's very hard to put the person back together again. Right? Very hard. And so, rather than become surgeons, we want to become DSP engineers. We want to figure out a way to look inside people's heads, for example, without cutting them open. And the beautiful thing is what's called the miracle of tomography. How many people have heard of tomography? Show of hands. Okay, so write that word down, because this is a very useful idea. Tomography. So what's the idea? Very, very simple, actually. You talk about Fourier transforms, right? Okay. So here's the beautiful thing. Actually, let's get a volunteer from the audience. Much more fun this way. Okay. No, you stand there. That's perfect. And actually, you can do that now. So here's the basic idea. Or actually, I'll just do this here. You stand here. So here's the basic point of how tomography works. I would like to see inside Dr. Doe's head. Okay? Without cutting his head. Okay? So what I do is I shoot things through his head. That's all I can do, right? I can't look inside his head by cutting it. The only thing I can do is have some kind of gun, and maybe the gun shoots away. Maybe it shoots X-rays, or maybe it shoots gamma rays, or maybe it shoots magnetic radiation of some kind, or electromagnetic radiation. And what I can do is I can point this at a certain angle, right? And now I can shoot through his head. Actually, move over here a bit. Right? Yeah, perfect. I can shoot through his head, and then I can put a detector here. Does everybody see this? And now what I'll get is a profile through his head in this angle, right? And he has glasses which really absorb X-rays. So maybe I see very high absorption over here, but then in the middle he's very smart, so lots of absorption. But then in this part of his brain, he's very kind, so it's very soft in this part of his brain, and so it's very, very little absorption. Okay, so I get a profile. And then what can I do now? I can rotate and take profiles from many different angles. Okay, does that make sense? And the beautiful thing, the miracle of tomography, that you're learning about when you learn Fourier analysis, is that if you take these projections through the head, and if you take their Fourier transform, well, actually let me go back. If you take these projections through the head, and if you stack them up in a two-dimensional representation,
you need a pointer or chalk?
Here it is. So I took those projections through Dr.